Welcome to Breadboarding. This is video 14 in the Breadboard PC series, and this is a second video for the Monochrome Display Adaptor. So in order to build our basic floppy disk PC able to boot MS-DOS, we need an MS-DOS and IBM PC compatible video card. For the Monochrome Display Adaptor, I covered the introduction, the high-level overview of this in the previous video. So if you haven't seen that, I suggest you click on the link at the top of the screen at the moment, and that will take you to that video. This won't make as much sense without viewing that video first. So in the previous video, we covered a lot of the high-level design of the MDA card and some of the changes we're going to make to simplify it and to make it work with modern VGA compatible monitor. What we're going to do now is to review 8 of the schematics from the original IBM MDA documentation. 2 of the schematics were for the parallel port, which we're not going to include in this project. So the first sheet is really just the interface to the I/O slot. So this was a plug-in card on the ISA bus, and we don't really need to worry too much about that. The only interesting thing is here, there is an inverted reset signal here provided, and we go into the next page, there's another inverter producing the same signal, so not quite sure why they ended up with 2 reset signals. The default reset signal on Intel seems to be positive, so +5 for reset, whereas a lot of other designs use reset active low. Now generally in all these diagrams, what I've tried to do is where there's some sort of question about something may not be not unnecessary, but there may be some sort of query about it, I'll do it in orange. Red is generally stuff we don't need to worry about, and the green stuff is things that we are going to need to worry about. Now you can see over here that we had the 8 2114 4-bit by 1K RAMs. That's going to be replaced by 1 4K dual port RAM, and by having dual port RAM we avoid needing all of these address multiplexers because it has 2 lots of address lines and 2 lots of data lines, so that simplifies things quite a bit. Now this clock and timing logic here is really quite complicated, but fundamentally what there is a dividing the dot clock down to the dot clock is here 16 megahertz dot clock, and on VGA it's 25 megahertz, so that will be replaced by a 25 megahertz, and then this is currently dividing it down by 9. Now we'll simplify that and divide it by 8, and an awful lot of this red stuff here is all related to memory timing, to coordinate the access of the CPU to the video RAM, to try and eliminate sort of display interference, video snow. Now because we're using dual port RAM, then we don't need any of that stuff. Also there's quite a few bits here to do with delaying some of the CRTC signals going through things. Now because the CRTC has built-in capability for delaying this, we don't have to worry about this for most of them. The horizontal sync and vertical sync I'm not sure need to be delayed anyway. Certainly from my experience in the earlier designs, that wasn't something needed to do. So this circuit is going to be fairly substantially simplified. We've basically just got a character clock coming out there, which is dot clock divided by 8. There is a write enable that's basically just the memory write, and Q5 output there basically is the signal that's going to be used for triggering the loading of the shift register. There is a jumper here, jumper 1, which complicates some of the diagrams, and basically this appeared only to be used for internal use by IBM testing, so we can ignore a large amount of the complications of this. So anything related to jumper 1 we're going to ignore, and this chip down here, for example, got the clock oscillator clock and various other settings depending on what the jumper setting was. So some of these areas in red we can just ignore altogether. It just complicates the understanding of what's going on. So the address decoding and the status port. So you can see here the status port gives us the current, whether or not the horizontal sync, vertical sync is active or not, and whether or not it's actually outputting anything in the video. We will actually need a lot of that logic, and basically it's providing decoding to these I/O ports. However, we can probably do a lot of this in programmable logic devices, which will reduce the chip count quite a bit. This down here is a CRTC status port. It basically just provides the status of the horizontal sync and the video output. The attribute video control takes the attributes out of the RAM, and there are actually a couple of latches here which I'm not sure we need multiple latches for the purposes of what we're going to be doing. What this basically does is decodes the attribute information, and these chips down here are basically working out whether or not we need underline, whether we've got reverse video, whether or not there's no display. So if it's 0000000, then there's no output. And basically the underline also has a look at the raster addresses. So basically only outputs the raster address. I think this is for row 12, I think it is. So this basically decodes which of the lines we're currently on of the character image, and it only outputs underline on a given row. So you can see there's an output there for underline. And the full output of all this basically says is, do we need to provide the intensity, bright output for the background, for the foreground? Alpha dots basically says, are we showing foreground or background? And there's another output here similarly. So this is really the output of all of this sort of stuff, and coming into here will also be the dots. So these are the dots coming in from the shift register and the character generator. So this is the output of the characters for the display, and it all feeds into here. So again, a lot of this will all be possible to probably consolidate down into one or two programmable logic devices, and we can simplify it quite a bit. There's also some logic up here that takes the video sync frequency, which in our case will be 70 Hertz, divides it by, I think, 32, and the blink frequency, which is used for the blinking video, and the cursor will in fact be the vertical frequency divided by 32. So the data buffers and latches we don't actually require at all. Because we're using dual port video RAM, this requirement disappears altogether. And then this is the video output and the CRT control port. So CRT control port provides a number of signals coming in. So we can see that the high resolution mode 0 should always be set to 1 anyway. So we can assume that this is always going to be 0 or 1. Bit number 1, although it says is not used, is actually can be used for determining whether or not we're using black and white or color. And then number 3 is video enable. So this will allow us to turn off the video output. And again, the IBM advice was, when changing the CRTC register values and things, then you should really disable the video output to avoid damaging monitors and things, which could have been damaged, I guess, by running at wrong frequencies. And then there's the enable blink attribute here. So if enable blink is set to 1, then the characters will blink, and they will use the bit 7 from the attributes. So if we look here, you can see that bit 7 in the attributes here was blink. But if blink is disabled, then that attribute is used for the intensity for the background. I would imagine most people would be more interested in having intensity for background rather than blinking, since I think most people would generally agree that blinking video is quite disturbing. So this is the output, taking the dot output, the various horizontal sync, vertical sync, and various other things, and then sending this out to the 9-pin D-shell connector. Now for this, a lot of this will be taken care of by our video digital analog converter palette, and the output here will just be going to our 15-pin VGA connector. So the character generator, we'll be using an EPROM for this. We'll be using a VGA character design, so that will be 8 bits across by 16 rows down. Some of the logic around here was related to, by having 9 pixel wide characters, there's certain graphics characters in this range here that needed to have the 8th bit extended to the 9th bit, and a lot of this red down here is all related to that logic to stretch certain graphics characters by their extra bit. So the right hand character bit to widen graphics characters. So a lot of this red here is stuff that by doing 8-bit wide characters, then you avoid all of that. So it's not completely visually compatible with the MDA, but from a programming point of view and a hardware point of view, it will look identical. It's just that we won't be messing around with this 9th bit, which causes quite a bit of complication. So basically what comes out of here, there's a latch from the character video RAM that drives the upper address bits for the EPROM, and then the CRTC row address 0 to 2 drives some of it. There's a bit of complexity here as well, in that this is actually the row address 3 but goes through some multiplexer. And again, I would say that we can probably simplify this quite a bit by wiring this one down into here. And so we're going to change this around a little bit. The reason for this, I think this ROM was also used for the CGA cards as well, and there was a complication that isn't required here. So that's a fairly detailed run through the schematics. So we can see here that the 9-bit wide characters causes quite a bit of confusion there. All this logic down here is again related to the 9-bit wide characters as well. So these red bits that we're excluding will simplify things again. this output here again is related to the 9-bit wide characters. So well, hopefully when we do the schematic, we'll see that we've been able to simplify this quite a bit, and the number of chips will hopefully be reduced from, say, 66 down to probably half that number. So what I have tried to do is to summarize that information in a diagram similar to what I did in the original video controller series. This MDA video display diagram, we're basically talking about the main computer data bus and address bus. We're using the 6845 compatible cathode ray tube controller. This is then being used to generate horizontal sync, vertical sync signals for the timing of the pages and the lines on the display. Display enable blanks out the output during the horizontal sync and vertical sync periods, and the cursor provides the timing for where the cursor is on a particular screen. That's driven by a 25 megahertz dot clock, which is then divided down by 8 to provide the character clock. So this is the character clock that controls moving from each of the video memory addresses. Then the CRTC generates the video address timing for the dual port video RAM, and dual port video RAM just means that the RAM can be accessed by the CPU at the same time as the video controller without interfering with each other. As I was saying, because we're using the same 4K RAM to provide both the attributes and the character data, we need to actually switch the lowest address line between character and attribute data based on the dot clock divided by 4. So this effectively runs at twice the frequency as a character clock, will be about 6.2 megahertz, and just means with the video RAM we've got is fast enough to be able to switch and provide the data in sufficient time to be able to output each character. Each character requires about 320 nanoseconds to display, each dot being about 40 nanoseconds. So we're doing 3 characters every microsecond. The character data for the dual point RAM, as I explained, is then used to determine the top 8 address lines for the character generator ROM, and the CRTC raster or row address determines the lower 4 address lines. That just chooses which line of the display of the character we're doing at the moment. And then the output of the 8 bits of the raster image from the character generator ROM is loaded into shift register by a shift register latch timing. Then the shift register is clocked by the dot clock, so it basically then shifts each of the bits out for the foreground background, whether we're showing a foreground or background, to our attribute control. And then the attribute data is going out to another latch. This contains the inverse video, underline, intensity information, or could be used for red, green, blue and intensity if we were using color mode. Then, in addition to the attribute data coming out, we've got the cursor information, and that's all going into multiplexer to determine whether or not we're showing the foreground or background color. And even when we're in monochrome mode, we have basically 4 video levels. We have black, and then we have the brightest green, and then we have 2 levels of intermediate green. So even in monochrome mode, there's effectively 4 possible output colors. And then we're going to use the video digital analog converter, and this allows us to configure the red, green, blue values for each of the input values here. And then this is then able to output to the VGA connector, and we'll also include the horizontal sync and vertical sync. And finally, the port information for the CRTC and the control and status port is identical to the original PC. Because we're adding the VGA palette, we're going to make use of some of the unused ports here. Now, what this means is that in the video section of the BIOS, we'll need to initialize these and to put some basic palette information in here as part of the BIOS. As long as programs are making use of BIOS calls to do this, it shouldn't actually cause any compatibility issues. These registers are generally not used within the address map, from my understanding. So I've updated the block diagram slightly. I've changed some of the names of these PLDs here. So attribute multiplexer, video out, clock, and also because we've got the blink clock coming from the vertical sync, I've also added an extra blink clock coming into here. There's actually 2 PLDs doing the clock, because we need, each PLD can only have 1 clock driving it. We need one to be driven by vertical sync and the other to be driven by the dot clock. So we need to have 2 PLDs there. So let's have a look at the schematic diagram as it is at the moment. It's still in draft at the moment. I've still got a few things to do to it, but I thought I'd show you in outline what it looks like, and then we'll finalize it when we've actually got to the end of this stage of the project. So this is the MDA Monochrome Display Adaptor part of the circuit. If we look at the overall diagram, you can see over here, this is where the processor is, and the LED display, PIA, RAM, etc. There's a few other bits here, like the interrupt controllers and things that I'm working on at the moment. And then down here, we've also got the keyboard, PS2 keyboard and mouse interface here, which I'm also going to be incorporating into this version of the diagram. But if we just look at the MDA adapter to start with, the first thing you'll hopefully notice is, compared to the 66 chips that the original MDA card had, then we're actually got substantially less. So we've got our dual port RAM, the character latch, the status register. This is an I/O port decoder, so an address decoder. This is our character ROM. This is a shift register that takes the character ROM and serializes it. This is our cathode ray tube controller chip. Then we have the video digital analog converter DAC. And this is our control register. This is one PLD, so this is the clock PLD. This is the 15-pin VGA connector. Then down here we have, this is the attribute latch. So this is coming from data coming out here. Then this PLD down here is related to the blink clock. So this basically takes the vertical sync, divides it by 32, and also buffers the horizontal sync and vertical sync, and actually feeds that into here. So in total, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And if we count the oscillator and the constant current source, then that adds another 2 on there. So I think that's 16 in total. So if going from 66 down to 16 was a lot better than I thought it would be. We may still need to add 1 or 2 things as we go through into the project, but the main complexity here is the PLDs that we've got. The I/O port decoder takes a new signal that I've put on the main address decoder that just tells us whether or not we've got an I/O port with the top address lines from A12 to A19 are all 0, and that all I/O addresses shouldn't be using that range. So this is just a signal that says we should have an I/O address with all the top address lines 0. And then we've got outputs here for the various CRT status control registers, the CRTC 6845 chip select, and then we need to do 2 separate signals for the palette video DAC, a write signal and read signal. Then the clock here takes in the 25 megahertz clock. It then generates divide by 8, divide by 4, various signals we need, and also all the latch signals, and buffers the dot clock as well. So we're driving the rest of the circuit off the buffered dot clock here. So that's the clock circuit. Control register provides things like blink enable, black, white, color, video enable. This is our video palette. So this drives the monitor directly through the red, green, blue output here. It has the data bus for connecting to the rest of the PC for programming it. And then for the moment, we're just feeding in 5 output addresses from the attribute decoding. So we're going to use the P4 line will tell us whether we're using black and white mode or if we're in color mode. And then the other 4 lines will then determine either in color mode what the color is. And if we're in black and white mode, then we'll just be using the bottom 2 bits for on and off and intensity on and off. These 2 PLDs include most of the complexities of the decoding of all of the various signals. So it takes the attributes out of here and produces various signals that we then feed down into here for determining whether or not we're going to show dots or not. S dots here is in fact the output of the shift register. So the shift register here is taking the output from our character generator ROM here. It's taking that out, feeding it into here, and then serializing this, and this is then determining, based on what attributes we have coming out of here, we're then actually telling the video digital analog converter which colors we want to show to the outside here. And then we've also got the horizontal sync and vertical sync coming from down the bottom here and coming into the port here. So it's still quite complicated. I'm sure there's a few mistakes on here, and as we go through building this out and we test it, we'll probably need to make revisions to this, and then what I'll also do is then merge this in with the rest of the diagram. But this hopefully is probably about 95% there of what we need. The other aspect of this that we still have to go through is what are all the rules and things for programming the PLDs. Okay, so that's where I'd like to break the video for now, and in the next video what we'll be doing is looking at starting to lay out the breadboard and starting to plug in the CRTC, the clock circuits, and see if we can actually start to get some video signals out of our connector here. Once we've done those basics, then we'll start to build out the character ROM, shift register, and then finally we'll add all the attributes, because the attribute handling is going to be the bit which is probably the trickiest to do. So if you don't want to miss out on the future updates to the MDA display adapter, then please hit subscribe. And if you found the content interesting, please hit like. It just helps to make the videos available to a wider number of people. Thanks for watching.